Is that going to be enough time? I could consider doing it till Monday if we really need to.
What did you change to the 31st?
You're supposed to turn in your redo of the midterm. Remember, you're supposed to not only
Mhm.
answer the ones you got wrong, but literally put the question down and then work out the whole solution for each problem, the entire midterm, and turn that in under midterm redo in week 10. That was supposed to be due today, but I changed it to the 31st,
Okay.
just to give you all a little bit more time. Oh, by the way, I noticed I found an error in the midterm, and then I made the change before you guys ever took it, so I didn't think anything. But y'all might find, and this is weird because it's literally not all the students, but few select ones somehow. And again, I have no idea how this happened. Have the word. There's one problem that basically is like a spherical shell, and you're asked to calculate the gravitational acceleration at a distance. I think it's like 4r away, and it gives you that the inner radius is like r and the outer one is like 3r. But in some random versions, it says diameter instead of radius. So if you see any of those and it says diameter, change it to radius. I changed it in everything that I thought should have it, but some reason it's still showing there. And not only that, I'm going to have to look back since I'm discovering that. I'm going to look at everybody's midterm grade in this class and see whether I need to give y'all some points on that, because that's obviously an error that's not fair to you guys. So you might actually be getting some extra points on your midterm. I just discovered that today, looking at one student's, his was still marked wrong, and everybody else's that I had seen so far was right. So I don't know how one particular student had it marked wrong, had it with the wrong word in it. But what I have discovered is that Canvas evidently is using pools of questions from pools that I've used in past courses, not just the course that I'm currently trying to make a test in. So when I found that typo from the actual textbook author, I went and changed it in my source, but now I know that they're actually pulling it from other sources, other courses, so I have no idea where it's getting it from. It's not supposed to be that complicated. I mean, I write code and stuff like that. I don't understand how a computer is doing this, but it clearly is. All right. Well, it's now time. So I'm going to ask you one more time. Does anybody have any questions? We're running about 3 minutes late. Not a big deal, but I just want to make sure anybody that has questions can ask them. Of course, you can also ask them at the end of class. But I did, since everybody's here now, I did push the midterm redo that you're supposed to turn in. I made that at 11:59 p.m. on Friday the 31st. So you've got a couple more days to get that done. If somebody really, really needs a little bit more time, y'all can probably contact me and I'll be glad to do it again, because you know me, I'm a pushover. But it's, the least I can do, because I haven't got all uh, the grade stuff sorted out and all that good stuff anyways. Well, it looks like no one has any questions for me, so I am going to go ahead and get started. What I want to do is I'm going to work a few problems. I know last time I was looking and I actually worked out. Hang on, where's somebody's calling? I'm going to call me right when my class starts. Okay, so basically, I did realize I worked out some integral r squared dm. In other words, I've calculated moments of inertia for you guys uh, in real time, and I did that for a rod. I think I did it for a rod spinning about its end. Then I used the parallel axis theorem to show you what a rod would be, what its moment of inertia would be if I rotated it about the center of mass of the rod. And I want to say I did another one as well, but I might not have. I thought I did a cylinder, but either way, I've definitely shown you that. There's also ones that I've calculated and put on my YouTube channel, and I think I gave you links to those. If you look in week 11, you'll see calculating moment of inertia, a thick cylinder, and calculating moment of inertia, a uniform rod. So they're actually there. And then I've got another one with I got another one with the parallel axis theorem. So that's all up there. So you do have, plenty of opportunities to see them. What I want you to do now is I'm going to show you how to solve some problems, and I'm going to introduce you to a way to do some problems that aren't so easy to do, but we can do them because we can use conservation of energy. So first off, I'm going to share my screen. Again, feel free to ask me questions at any point. Okay, so sharing my screen now. Okay. So the first thing I want to do is I'm going to make use of some of the dynamics type problems that we're working. And what I want you to imagine is a pulley that actually has mass. So I think last time I had actually worked the Atwood machine and then left the rest of it for you to do as a extra credit. So that's still fair game. But I'm going to do another one, and it's important for you to see this one so you'll see how there's a difference. So I'm going to do two problems that look fairly similar, but are just a slight little nuance difference about them. So here goes. I'm going to imagine a pulley that has a mass. Let's say M is equal to, let's say 5.00 kilograms is the mass of the pulley. That's just horrible. I've never seen handwriting that bad. 0.00 kilogram is the mass. And someone else just came in. Got that. Okay, and let's say the radius. So this has a mass M and a radius R. Let's say the radius is in fact R equals let's say R equals 20.0 centimeters. Okay. Now, in addition to that, there's going to be a torque due to friction. And that torque due to friction is going to be 2.00 meters times newtons. And what I'm going to do is I'm going to hang a mass. Actually, I'm not even going to hang a mass. I'm going to pull down on this with a fixed force of F equals, let's say 20.0 newtons. Okay. And I'm going to tell you that it's going to start rotating from rest, and therefore omega 0 is 0, and it's going to reach a final angular speed of, let's say, 30.0 radians per second after a time of delta t equals, let's say 4.00 seconds. Okay. So that's all the data I have. And what I want to do is I want to find out what is the moment of inertia of the pulley. Okay. Everybody sort of understand what the problem is? All right. So I'm going to go ahead and I can use this diagram as an actual free body diagram. I should probably indicate that this is a friction torque. Okay. So the force that's actually causing this thing to rotate is a fixed, what did I say, 20 newtons? It's a fixed 20 newtons right here. And the torque that is due to friction is actually tending to act that way. So for my solution, I'm going to employ the summation of the torques is equal to I times alpha. Okay. And obviously, I can use some kinematic equations to figure out alpha because I have omega and omega zero there and delta t. And not only that, I am allowed to use this equation because we see that the axis of rotation goes through the center of mass of the pulley. I want you to recall, or at least look for in your book in chapter 10, where they tell you when it's okay to use the summation of the torques is equal to I times alpha. He takes the time to explain that to you. That's something you need to read as well, even though I did tell you initially what it was about the axis of rotation. So let me go ahead from this quote unquote free body diagram. Let me go ahead and put that into the equation and start working it out. So I'm going to assume that a rotation in the counterclockwise direction is positive. So I will, in fact, have a torque that is actually positive F times R. Okay. So that's the R that I wrote up there, and that's the F that I wrote up there. That's an actual counterclockwise torque, so I'm causing that positive. And then the torque due to friction is negative, so I'm just going to put tau sub friction right here, and that's equal to I, which is what we want to know, and alpha, which I can compute. So now, before I plug the numbers in, I need to know what alpha is. And it turns out that alpha, if it's a constant, or if it's not, I can just calculate the average. But in this case, I think we're leaning towards it being an actual constant. So that is just plain alpha, and that's equal to omega minus omega zero over delta t. We can see that that's going to be 30.0 radians per second minus 0 radians per second divided by 4.00 seconds. So clearly this is going to be 7.50 radians per second every second. And again, I'm using that wording that I taught you about early on so that we'll have some sense of what the acceleration means. So what this is telling me is that if I allowed this thing to go from rest, after 1 second, it'd be rotating at a rate of 7.5 radians per second. Remember, 2 pi is 360 degrees. So 2 times pi would be 6.28. So it's a little bit more than 1 rotation per second is what the velocity would be after 1 second. And then after 2 seconds, it would be 15. And then after 3 seconds, it'd be 22.5. And after 4 seconds, it'd be 30. So that's how the acceleration is actually worked out. Now I'm going to put in the numbers into this RF minus TF is equal to I times alpha. So the R, of course, I need that to be in actual meters. So I'm going to say 0.200 meters times 20.0 newtons minus the torque that I said was 2.00 meter newtons is equal to I times 7.50 radians per second per second. Obviously, this is a bit of a problem. Let's do this. Okay, I'm trying to now cut this. Now I'm going to paste that. Okay, so I've now moved it out of my way. All right. So 7.50, I also accidentally put that there, so I'll get rid of that. So 7.50 radians per second. Now I can see that basically 0.2 is the same thing as 2 over 10. So if I multiply, or if I take 20 and divide it by 10, I get 2. And then I multiply it by 2, that's 4. So I get 4.00 meter newtons minus 2.00 meter newtons is equal to I times 7.50 radians per second. And I can say that I is going to be, obviously 4 minus 2 is just 2. So I'm going to say it's 2.00 meters times newtons divided by 7.50 radians per second. Now that's the same thing as 15 over 2. So I could say that's 4 divided by 30. That doesn't really help me that much. I guess I'll just suck it up and use a calculator. So when I do this, I'm going to say 2, and by all means, please check my work if I made a mistake. 2 divided by 7.5. If I made a mistake, it'd be helpful for you to let me know. Now, when I divide 2 by 7.5, that radian just disappears. But remember, a newton is a kilogram meter per second squared. So I'm dividing it by per second squared. So that's just going to cancel out, and I'm just left with kilogram meter squared. And in this case, I get 0.2667 kilograms times meter squared. So that is the actual moment of inertia. Whoa. That is the moment of inertia for this pulley. Now, a typical pulley is often like a more or less like a cylinder. So I should, given that I know the mass of the pulley is 5 kilograms and the radius is r equals 20 centimeters, I could see if this is a reasonable answer. So I'm going to do that. What I found out when I did a cylinder is that I for a cylinder is equal to 1/2 mr squared. So let's compute what this would be if it's purely a cylinder. Now, obviously, pulleys are never purely a cylinder, but this might be an approximation anyways. So I'm going to do 5.00 kilograms, and I'm going to multiply that by 0.200 meters, and that's going to be squared. That's 2/10 times 2/10. That's obviously 4/100ths. If I divide 5 by 100, then that's going to be 0.05. If I multiply that by 4, that's going to be 0.2. And therefore, I get 0.100 kilograms meters squared. Okay. So that's what that would be, again, assuming my arithmetic was right. I do expect in general that a pulley should have a little bit more moment of inertia than a cylinder, just because normally when you make a pulley, it's going to have a good amount of weight right at the center, but the majority of the weight will be around the outside edge. So the fact that this is in the same order of magnitude, around 0.1, that's pretty good. And the fact that it's a little bit higher, the actual moment of inertia is a little bit higher than just a pure cylinder, that's also fairly reasonable. So that's just a good technique to do when you're solving physics problems, is try to make sure it makes sense. A guy by the name of John Archibald Wheeler, who is one of our superheroes of physics. He's sort of this guy that happened to write like 3 papers. Literally in 3 different cases, he missed the Nobel Prize because he published it within about a month too late. So he really was a brilliant guy. Could have been perhaps a Nobel laureate, but he just missed it a little bit. And he wrote, one of the best books on general relativity. But anyways, one of the adages he always said was, never solve a physics problem whose answer you don't already know. That's actually a really good piece of advice if you understand it. It's a little hard to do right now as a first-time physics student. But basically what he's saying is, take a poke at what you think the answer is going to be. And then when you get the answer that you calculated, you can compare it to the answer that you guessed it was going to be. And in that case, if it's really far off, you look and see if you made an error in your problem solving. If you did, that's going to catch the error. But if you didn't, then there's an error in your understanding of physics, and you need to correct that too. So it's a really nice thing sometimes it can be just interpreted as make sure you check it after the fact. And that's what I was doing here, was just checking it after the fact. I would have probably did this little quick calculation beforehand, but because I've solved this problem like 3 times today already, I didn't think to show you guys me doing it again beforehand. But
So we get the 0.1 and we compare that to what?
to the 0.2667.
And it's supposed to be smaller always?
No, I would expect the one for the pulley to be a little bit larger, because if you look at a pulley, it's normally like it's got a little hinge, and that's got, I mean, a little axle, and that's got a little weight there where there's bearings, but then it just becomes a thin little piece of plastic until it gets out to the edge, and then there's a rim
Yeah.
of plastic. So more of the weight, I think, is distributed far away. And remember, the formula for actually moment of inertia, I is equal to the integral of r squared dm. So the fact that the mass would be distributed further out means that's going to make a big difference in the moment of inertia.
Yeah, so the inertia of a cylinder should be smaller than that of a regular pulley.
Of a pulley, yeah. Just as
Okay,
a rule
thank
of
you.
thumb. Now, I wouldn't expect you guys to know that off the top of your head, but I certainly would expect you going forward to think of that. And just from looking at pulleys, I think you've probably seen enough pulleys where you see there's like this kind of shape around the outside edge. That's where the rope or whatever goes in. And then it's just a flat piece of circular plastic going into the hub. And then the hub has some bearings, but the radius on those is so small that that's going to be a fairly small contributor. Does that make sense?
Yes.
Okay. Yeah, and again, this is thinking that way is a little bit higher level than you're necessarily expected at this point. So don't feel too bad if you hadn't thought of it ahead of time. That's perfectly normal. If you don't understand it now that I've explained it, then that's where you want to get help for. Okay. All right, so now I'm going to teach you another big rule here. And this is basically where I'm going to take exactly the same scenario, but I'm going to change it just a little bit because I want you to understand something that it's really hard for students to get. For instance, what I said was there was a force of 20 newtons on that. I'm going to now hang a mass of 20 newtons from that and see, or let you see that it's in fact quite different. So let's see what that is. All right. Yeah, I think that's about right. Okay. Okay. So let's look at another problem. I'm going to take exactly the same pulley, using the same pulley, a 20.0 Newton bucket is hanged from the cord, and the friction is unchanged. What is the acceleration? Oh, I'm going to write this as accelerations A and alpha. And what is the tension force? Okay. Assume. Oh, I just. Assume the cord does not stretch go slack or slip. Okay. So we basically have the same scenario, but there's a minor difference. So let me draw the diagram here. So the diagram is, again, we have a moment of inertia. We have a moment of inertia that's equal to, what did I get for the last answer? 0.2667, 0.2667 kilograms meter squared. We also have that the radius is 20 centimeters. Whoa, nearly. And the mass is equal to 5.00 kilograms. Okay. Now, what I'm going to have here is a string pulling down on it. And then we have a mass whose weight is 20.0 newtons, which, by the way, implies that M is equal to 2.041 kilograms. Okay. We also have that same torque due to friction acting on it. Okay. And that torque is, of course, equal to 2.00 meters times newtons. Make sure that's the right number. Yes, it is. Got that, got that. Okay, so this time I'm going to actually try to calculate the acceleration, which last time we figured out was 7.5. Okay, so I'm going to first draw a free body diagram of the pulley. Okay, and what that entails is this plus a little force acting on the end. And of course, this is R. And we also have, of course, that friction acting that way. So here's my solution. Let's do solution in red this time. We're using the summation of the torques is equal to I times alpha. And since it actually said the cord's not going to stretch, it's not going to go slack, and it's not going to slip, what that means is if I pull that rope down 1 inch, then a spot on the outer edge of that pulley is going to move exactly 1 inch. And not only that, that also means that the acceleration tangentially is equal to R times alpha. Okay, that's what rolling, or that's what not slipping does, because if the string moves 1 inch, then the outer surface will move 1 inch. If the string moves 1 inch in 1 second, then the outer surface of the pulley is going to move 1 inch in 1 second. And if the string moves 1 inch in 1 second at one point in time, and then 2 seconds later it moves 2 inches in 1 second, it's going to do the exact same thing on the outside edge of the pulley, so we can see that the accelerations are in fact equal. So that's why I can now say A equals R times alpha. Okay, but what we're wanting to know is we're wanting to know A equals question mark, alpha equals question mark, and tension equals question mark. So on this side, we have a tension T, and according to the summation of torques equals I times alpha, we can see that this is going to be T minus, or excuse me, RT. Notice the tension and the lever arm are perpendicular to each other. Okay, so RT is the torque minus the torque due to friction is equal to I, which we already know, times alpha. So I'm going to put these numbers in. Obviously, I can't put the tension in because I don't know that, but I can, for instance, divide both sides by R, and I'll get T minus 2.00 meter newtons divided by 0.200 meters. That's the friction torque divided by radius r is equal to 0.2667 kilogram meter squared over 0.200 meters times alpha. Okay. So I'm going to call this equation 1. Now you see what I did? I had RT and I didn't want to have that R out there in front. I wanted it just in terms of T. So I divided both sides of the equation by R. That meant the torque is going to be divided by 0.2, which is, by the way, 2/10. So that's the same thing as multiplying by 10 and then dividing by 2. So if I multiply 2 by 10, I get 20, and then I divide by 2, I get 10. So I can see already that that second term is going to be 10. So this would be, notice the meters cancel out. So that's 10.0 newtons is equal to, same thing happens here. I'm going to multiply 0.2667 by 10. That gives me 2.667. And then I'm going to divide that by 2. That gives me 1.33, basically 4. And that's an extra sig fig, of course. And that's just plain kilograms on this side times alpha. And I'll call that equation 1 as well. In fact, let me erase the other one because now I've got it in a better form. All right. Any questions on that part? Now I've got to draw the free body diagram for the hanging mass. And of course, I've already decided that whatever makes the pulley rotate counterclockwise is the positive direction. So that should mean that the weight going down is the positive direction as well. So my free body diagram is basically going to be a dot right here for a mass of 2.041 kilograms. This is going to be the positive y-axis. And in fact, I'm going to say this force right here is equal to 20.0 newtons, which obviously you can tell is M times G. But there's also a force of T back there. So the summation of the forces in the y direction equals mass times acceleration in the y direction gives me, in fact, 20.0 newtons minus T is equal to, notice, by the way, that the tension is not included on, the torque due to the friction is not included on this, because on the left-hand side, you could think of it as acting upward, but on the right-hand side, you could think of it as acting downward. But that's all acting on the pulley itself, nothing to do with the actual mass. So the only forces acting on the mass are the ones in the free body diagram. So I'm now going to write this as 2.041. Again, that one's an extra sig fig there. Kilograms times A. And that's going to be equation 2. Okay. So I can combine equations 1 and 2 to eliminate T by just solving, for instance, equation 1 for T. So 1 into 2 is going to give me, notice if I solve for T, that's going to be 10 plus 1.334 times alpha. So I'm going to say 20.0 newtons minus 10.0 newtons plus 1.334 kilograms times alpha. That kilogram turned out terrible. Let me fix that. All that times alpha, and that's the tension part, equals 2.041. Again, that part's an extra sig fig there. Kilograms times A. Okay. I can make this a little simpler by writing 20.0 newtons minus 10.0 newtons minus 1.334 kilograms times alpha is equal to 2.041 kilograms times A. All right, so now I can see I've got two unknowns, but I can actually use this equation right here, which I'm going to call equation 3. The A is equal to R times alpha. I can use that. So now I'm going to plug 3 in. That's going to give me, notice the 20 minus the 10 is just going to give me 10. Minus 1.334. I'm going to leave the units off now because we've seen enough how it actually works. This is going to be alpha. And of course, the A is equal to R times alpha. So that's going to be 2.041 times R, which is 0.2 times alpha. So now we only have one unknown. This is going to be 10.0 newtons is equal to, I'm going to pull all the alphas on the other side. That's going to be 2.041 times 0.2. That's 0.2041 times 2. So that'd be 0.4082. So 0.4082. And actually that's 2 sig figs beyond what we actually had, times alpha, and then plus 1.334 times alpha. In other words, I pulled the 1.334 alpha over to the same side and then went ahead and factored out the alpha. So alpha is just going to be gotten by taking 10 and dividing it by the sum of those two. So 10 newtons divided by, notice when I actually got that, this was kilograms times meters when you multiplied the 0.20 or the 2.041 times the 0.2. that became kilogram meters. So I'm going to divide this by what, 1.73, 1.742 kilogram meters. And of course, that just gives me radians per second per second. So I'll check my work while I'm at it. I'm going to do 0.4082 plus 1.334. That did give me 1.7422. So I feel pretty good about that. Now I'm going to do 10 divided by that answer. That gives me 5.73, or I might as well call it 5.740. And that's radians per second per second. Okay. So I now have alpha is equal to 5.740 radians per second per second. That's one of my answers. And of course, A is equal to R times alpha. That's going to be equal to 5.740 times 0.2, because the radius is 0.2. And that gives me 1.148. And that's meters per second per second. And finally, I can solve for the tension. Oh, I don't want to use that. The tension, you can tell, we can take it from equation 1, for instance. That's just going to be 10 plus 1.334 times the alpha. So I'm going to write that as my answer. I'm going to compute that as my answer. I'm not going to take the time to show it because I think y'all can see that yourself. And I'm running out of space on here. So I'm going to say 10 plus, I'm taking the 1.334, and I'm going to multiply that by the alpha, which was 5.740. That gives me 7.657. Now I'm going to add 10 to that. So I'm going to add 10 to that because equation 1 says 10 plus that's the actual tension. So I get 17.657 newtons is the actual tension. So the point of me doing this problem was that you'd see that, in fact, this is a very different problem. Even though we use the same numbers, when I said I had a force on the previous problem equal to 20 newtons, that's an entirely different scenario than having a 20 Newton mass hanging from it. A 20 Newton weight hanging from it basically only applies 20 Newtons to the pulley if the pulley's holding it up, but the pulley's not holding this up. The mass is actually causing the pulley to rotate. So you end up getting a tension that is in fact smaller than 20. That's why we see that it's 17.65. So we got a tension that's smaller, and then whatever's left is really the only tension that's on it. So that's about what, 2.35 newtons is pretty much all that rotated it. So we got a much smaller acceleration. In fact, the acceleration for the previous one was 7.50 radians per second per second. We got 5.74 radians per second. And I didn't even calculate A before, but you can see that clearly they're different. So any questions on that? No questions? All right. So that makes pretty good sense to everybody. All right. So there's another neat physical principle that comes into play here. It turns out that when an object, let's say like a smokestack sort of looks like a big chimney with nothing attached to it. They're all over tobacco country, for instance, and various other places in the United States where they use smokestacks to get rid of smoke from whatever burning processes they have. And if you're lucky enough to run into a demolition site of one, what you often see is a smokestack that starts to fall over when they're demolishing it, and it'll literally break in half. And the reason why is that the smokestack, though designed to handle lateral forces like from earthquakes and stuff like that, actually gets the lateral forces that exceed what it was designed for. And that's because you actually are forcing, when something falls like this, you're forcing the outermost edge, in other words, the highest part of the smokestack, you're forcing that to accelerate quite a bit greater than G, because the G is what's going to happen to the center of mass. So when you actually apply the weight to a smokestack, basically the weight is applied to the center of mass of the smokestack, which is about halfway up. And since the acceleration is equal to R times alpha, and alpha is the same for all parts of the smokestack, in other words, if the bottom's rotating by 5 degrees per second, then the top should be rotating by 5 degrees per second. Since that's the case, then when you multiply that by R, that radius is much larger at the top, and that actually causes an acceleration that's much bigger. So you're going to see that here in a couple different ways. So first off, what I'm going to do is I'm going to imagine a scenario where we're going to have a massive rod, for instance, hanging, or I should say propped up horizontally. And from that, I'm going to assume that gravity's acting on it, and I want to calculate the acceleration that it's going to actually have, at least at that instant. So let me draw the diagram, and that'll make a little bit more sense, hopefully. So what I have here is a little axle and a little hinge right here. And then this, of course, is going off to a rod. Like this. And what I'm going to say is this length is L, and I'm going to say at about halfway, this is the center of mass. And that's part of the reason in the last chapter why we started learning about the center of mass. Whenever an object is being acted upon by a force, basically what we're saying is that you can pretend like that object is being is having the force applied directly to the center of mass. And that's what we're doing here, because that's the way the thing will actually behave. Let me get rid of this. I drew that too long and it aggravates me. Whoa, wrong color. Okay. Now, what I'm saying with this being the center of mass is that this, in fact, is a uniform rod, so that if I go halfway over, I'll actually hit the center of mass. If this wasn't a uniform rod, maybe the right end was made of lead and the left end was made of balsa wood, then obviously the center of mass would be way over to the right. Maybe it'd be at 7/8 L or something. But we're going to assume that it's not, that it's actually a uniform rod. And what I want to calculate is what is A and alpha at t equals 0 seconds. In other words, right after I drop it. So you can imagine, for instance, that my hand is right here, and it's supplying the force necessary to hold it up. And I'm instantaneously going to move my hand out, and it's going to start to fall. I want to know what is the acceleration at that instant. And the reason why I have to ask that instant is because notice here, you're going to have a force acting right here, and that force is going to be the mass of the rod times G. And notice that, in fact, the lever arm is, in fact, exactly perpendicular to the force. But as soon as that rod starts to fall down, then the lever arm and the force are not going to be perpendicular anymore. So the torque is actually changing. So we're only going to look at that at the instant I let go. So when I let go. Okay. So what we know is, let's do the solution thing here. The summation of the torques is equal to I times alpha. Now, it turns out that the moment of inertia for a rod, so I rod about the end, is equal to, and this is one that I calculated for you in last class, that's equal to 1/3 m times L squared. And in fact, through the middle is 1/12, which we also calculated, but that's what we need because it's falling about the end. So I'm going to plug this in, and I'm going to see that the torque is in fact going to be m times G times L over 2. And that's equal to 1/3 m L squared, because that's the moment of inertia, times alpha. You can automatically see that this m is going to cancel out with this m, and one of those L's is going to cancel out with that L. And from this, I can immediately say that alpha is equal to, what's that, 3/2 G over L. And that is, in fact, the angular acceleration of that rod. Okay. Now, here's the tricky part. I need to find out what the, and I might not even stated this, come think of it. I want to know the acceleration of the tip. I think I started talking about it, but I never expressly told you guys. I want to know the acceleration of the tip. I started talking about that by saying the smokestack, the end is going to fall away faster because gravity's acting on the middle, and the middle is going to try to fall at G. But that part that's proportional to R is the velocity of the tip. So that's going to actually, or the acceleration of the tip, that's going to fall at a rate much higher than G. That's sort of the danger of being near falling trees, is you're used to seeing things fall and you know roughly how they behave. But when you see a tree fall, you're not used to that. The end of the tree is going to move a lot faster than you might think. So in this case, we're going to use A is equal to R times alpha to compute A, but I want to know A for the tip. So anybody have an idea what R to use? Anyone? Anyone? Bueller? Bueller?
Half L.
Okay. Half of L would exactly get you how fast this spot's going. Y'all can see my little arrow there, right? So if the radius, which is the distance from here to here, gotcha. Now you know what I'm talking about, Kamna?
Yeah, that would be L then.
Then L, exactly. So yes, the tip is going to require the radius to be L. So now what I can say is the acceleration of the tip. And this isn't that impactful right now, but it's basically going to be L times 3/2 G over L. So you see that the acceleration of the tip is in fact going to be 3/2 G. Now, that is a pretty neat thing, because normally when you drop objects, they fall at a rate of G. You know, that's the acceleration. This one's 1.5 times G. So that does actually show us what we need to see, that in fact the acceleration is going to be larger. But when it's all said and done, we can't analyze this all the way till it falls horizontally. We can't do that with this. In fact, if you wanted to, what you could do is you could allow, assume this is going to fall through 1 degree, say, or I wouldn't use a radian, but maybe 1/10 of a radian might be decent. But you assume that the torque is going to be a constant over 1 degree, because 1 degree is not that big a change. You then use that acceleration, which is in fact 3/2 G over L, to calculate what its speed will be at the end of that 1 degree. Now you calculate again using the actual theta that you have. Instead of this thing being horizontal, it's going to be pointing at 1 degree below horizontal. And you now calculate it with that torque at that angle, and you get a new alpha. You take that alpha and compute what the final V will be at the end of that degree, and you can keep doing that until you got through all 90 degrees, and that would give you a pretty good estimate. Ideally, we would like to actually solve that without that discrete method, but it turns out that's actually going to require an elliptic integral, which is a god-awful thing that you won't even cover normally in your differential equations class, because it is actually solving a differential equation. Only the differential equation is a type that doesn't lend itself easily to solutions. So what could we possibly do? Well, what we can possibly do is use something else. Specifically, remember I told you the paradigm where we're going to use all these vectors and we're going to use F equals ma. But then once we got done with that, we switched to getting rid of vectors, except in the little parts of the problem, and used methods of energy. Well, that analogy that I told you about last time between rotational motion and linear motion can help us a lot. So I'm going to reiterate some of that. So for instance, we learned that work is equal to the integral of F dot dl. But what is the rotational analog to force? In other words, what quantity causes rotation? Anybody recall?
The torque?
The torque, exactly. So guess what? You can actually change this to torque times. Now, what takes the place of X, for instance, in rotational motion?
Or
Close. I mean, that is actually one that has the right units. But remember, we had X equals 1/2 AT squared plus V0T plus X0. What did that become in rotational motion? Do you recall?
Beta?
Yeah, there you go. So guess what? This is going to become torque times d theta. And yeah, you ended up stumbling upon the right answer. You can also realize that power is equal to, let's get rid of that a second. It's equal to dw over dt. If you look at the w above, you might interpret that as F dotted with dl over dt. But can anybody tell me what you think dl over dt might be? Just in case you don't remember from when we covered this material. What's the units of dl over dt?
That'll be meter per second.
Yeah,
Which is
meters per
speed.
second. So that sounds like a what?
Speed,
Exactly. And in fact, if I want to make it a vector quantity, I'm going to say it's F dot V.
velocity.
Yep. So guess what? There turns out to be yet another formula for power for rotational motion that is instead torque times omega, where omega, of course, is d theta dt, just like V was dl dt or dx dt even. Okay. So those are some neat things that happen. Now, if you play with these a little bit, you can, for instance, calculate sort of the equivalent of a work energy theorem. And of course, the work energy theorem said that the work total was equal to the change in kinetic energy. Well, that happens to give you exactly the same thing over here. Work total is equal to the change in kinetic energy. Only the kinetic energy here, instead of being kinetic energy equals 1/2 mv squared, the kinetic energy over here becomes 1/2 I omega squared. So now let's look at the same problem, but using conservation of energy methods. So the energy method that I taught you guys was this. I said work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. Okay. Now, in this case, I'm sort of ignoring people putting work in and friction and stuff like that. So I'm going to say this is 0, this is 0, this is 0. And in fact, I'm going to attack that same problem, specifically that beam right there. Now, we're going to have to treat the object as if it's a point object at its center of mass. So right now, if this thing were allowed to be comfortable, in other words, my hand was to move and I just let that rod sit where it wants to, it would sit in the vertical position. And how far below the axis of rotation there, how far below that it would be the center of mass? So I'm imagining in this case, the rod is down like this. And what I'm asking is, how far down is the center of mass? Again, that red thing's supposed to be the same thing as the blue thing. Obviously, it's not the same size, but I was trying to pretend like it was so I could fit it in. I do know that this is L. Kamala, do you know how far the center of mass will be below that?
I got distracted a little bit.
That's okay. You've been bailing me out or most of the night, so that's all good. I think you will agree with me when I tell you it. Since the whole length of this thing is L, the center of mass is L over 2 away. So the center of mass should be L over 2 down. So the reason why I'm asking that is initially it's sitting perfectly still. So this is 0, but the potential energy, in fact, is going to be M. Actually, I need to switch this to blue. It's going to be M times G times L over 2. Because basically I can count this as u equals 0. Obviously, that's a different problem, so I don't want to write that on this particular problem, but that's what I'm doing is I'm pretending when the center of mass is down here, that's where the potential energy equals 0. And obviously, when the rod is horizontal, the center of mass is L/2 higher. So that's why I use that. Now, on the other side, the potential energy is going to reach 0 because it's in its comfortable spot, but the kinetic energy is in fact going to be 1/2, is going to be 1/2 I, which rotating about the end is 1/3 ml squared times omega squared. So in other words, this is 1/2 I omega squared. So this is how conservation of energy works in rotational motion. Now, in this case, we actually just have one thing rotating about its center. If you had, for instance, a disk rolling down an incline, then you'd have the center of mass moving at a velocity v, so you'd have a 1/2 mv squared, but you'd also have a plus 1/2 I omega squared. So you got to keep that in mind when you start to do other problems. But the main thing is I wanted to show you exactly what this part is. So this is 1/2 I omega squared. Now you can see that the 1/2 and the 1/2 are going to cancel out, and the m and the m are going to cancel out. And you can see that the exponent of 2 on the L is going to cancel out completely with that. And what I'm going to get is just G is equal to 1/3 L omega squared. So omega is going to be actually equal to 3G over L square root. Now, that's the angular velocity with which this thing will be moving when it gets vertical. So what I mean by that is here's our little hinge. Oh. Here's our little hinge. And this thing is moving, in fact, at a rate of omega equals d theta over dt. Now, this part moves that fast. So does this part. So does this part. So does all these parts move that speed, or else the thing would get bent and stuff like that. But what I want to know is what is the tangential velocity right here. So we know in general that V is equal to R times omega. So what R are we going to use to calculate the velocity of the tip? How far is the tip from the center of rotation? Anyone?
L?
Yes. So we're going to write L here, and then we're going to write omega there. So, and this whole thing is I'm going to actually compare this to dropping an object from, say, the same height, the height of the axis or the axle, and let it fall to the height of the tip when the thing is sitting vertically. So what I get now is that V tip is equal to L times omega. Well, omega is the square root of 3g over L. So if I pull the L inside, that becomes L squared. So I'm going to say 3g L squared over L in square root. Well, that is V tip is actually equal to the square root of 3GL. That's the actual velocity of the tip, which is what I wanted to know. And this is actually the angular velocity. Now, let's say I had a rock right here of mass M. Obviously, it's that same height here, and I let it fall all the way to here. Let's use conservation of energy to find out what the velocity of the mass equals right there. Okay, it's falling from rest, but I'll use conservation of energy again. So the conservation of energy for this one's going to be work in plus U initial plus K initial is equal to work out plus U final plus K final plus E loss. Now, in this case, that's going to be 0. That's going to be 0. That's going to be 0. And in fact, we can make this part right here U equals 0. And this part up here, kinetic energy initial, is equal to 0. So I can go ahead and say this is going to be 0 and this is going to be 0. So the potential energy, at least at the beginning, is going to be M times G times obviously this height, which is L. And the kinetic energy is going to be 1/2 M V squared. And that's the sub M that I was talking about. You can obviously see that the M is going to cancel out. And what we get is VM. Actually, what we get is the velocity of the mass is actually going to be the square root of 2GL. So this is what I was talking about. By an object actually rotating about its end, it's actually going to move way faster than you'd expect by your knowledge of gravity. In fact, if you dropped an object from the height of that axle and then you let it fall to the height of the tip of the beam when the beam is vertical, it's only going to be having a velocity of the square root of 2 times G times L. Whereas the velocity of the tip of the rod is actually going to have a velocity of square root of 3 times G times L. Does that make sense to you guys? I mean, not necessarily that you understand that it should be that way, but can you see how it turned out that way? Anybody have any questions on that? Okay, so I think we're all pretty good on that. Let me double check. This is the notes from last time. Yes, I did calculate the moment of inertia for the center of mass and for it calculated about the end. And I think that was, oh, yeah, I also did it for this one for a cylinder. So yeah, I did calculate all that. I also showed you these other equations, work equals torque times d theta. Okay, I just wanted to make sure I'd done all that. So all that, I mean, I've actually given you enough here, and you can tell if you look at the homework sets, you'll see that the conceptual questions are due Sunday. Or I think for you guys, it might be Monday because y'all are Tuesday, Thursday. No, you're a Monday, Wednesday class. So yeah, it should be due Monday. And then on Wednesday, the calculational problems are due. So y'all should have plenty of time. There is another concept. Well, there is another set of problems that you need to be able to solve. I didn't really show you this, but your book does quite a bit of work with it. And that is, for instance, rolling without slipping. So if you, for instance, had a disc rolling down an inclined plane without slipping, then you could use energy methods again. You could also use dynamics methods to, for instance, calculate what friction force is necessary to actually be sufficient to make the object roll without slipping. Because obviously, if you have zero friction, then an object sliding down an incline is literally just going to slide down the incline instead of rotating. But once friction gets in, then that friction is going to tend to make the disc rotate as it goes down the incline. And if I had enough friction where every inch that it rotated, it actually went down an inch on the incline, that would be rolling without slipping. So your book goes in section 10.9 over that pretty much ad nauseum, but it's pretty straightforward calculations. I think I've sort of handled the tougher stuff here, and you could probably see other examples online, or I think I even have a couple on my YouTube channel as well. You can do a search for rotation, or you can do a search for rolling, that sort of stuff, and that'll pull up the videos. But like I said, you can also find examples in your book. I always, like when I take an online class, if I was sitting in an online class, at the end of a chapter, like right now, I'm telling you, we just finished chapter 10. I would immediately go to the end of chapter 10 and look at the exercises and start trying to choose odd problems, because those answers I know are in the back of the book. And I'd specifically look for odd problems that are like the ones that are giving me difficulty. And then I'd try to solve those and then compare the answer. That's a good thing to do, and that's a good way to work. But anyways, I will go ahead and let you guys go. We've got technically 3 minutes left till class is over, but you're all, of course, free to go. And go ahead and don't forget to turn in your redo of the midterm so you can get extra credit points. And I will see you guys again on Monday.
You said you changed the due date for that, right?
Yes, I moved that to Friday at 11:59 p.m.
Okay.
Let me know if y'all need a little bit more time. I could probably work it for you.
Professor Younger, did you say the homeworks for chapter 10 were due Monday and Wednesday?
I think it's Sunday and Tuesday maybe, but let me double check.
That's what the due dates say.
Okay, yeah. When I was thinking you guys were my Tuesday, Thursday class, that's why I was coming up with Monday and Wednesday. But thank you for clarifying, because I probably did screw that up.
So the due dates are correct?
Yes. Yeah, I just wanted to give you a little bit extra time. Normally homework's always due for my Monday, Wednesday classes on Sunday night at 11:59. I actually put just the concepts due on at Sunday night, whereas the actual calculational ones are due Tuesday night. So hopefully that'll give you a little bit more extra, a little extra time, make you not feel so stressed.
All right, thank you.
You're welcome. Have a good one, George.
Is chapter 11 still due on Sunday as well? Or?
We haven't covered chapter 11, so the date's going to change. Don't worry about that. Remember, if I haven't covered a chapter yet, you're definitely not responsible for it.
Okay, thank you.
No problem. Anybody else?
Excuse me, how many points did you say the max we're getting from the redo, from the midterm redo?
So basically what I've probably decided on is people that make less than 50, 50 or less are probably going to get 20 points, up to 20 points. And people that make, let's say, 80 or less is probably going to get 10 points. And maybe people that made higher than 80 will get 5 points if they want. So that's what I'm leaning towards right now.
Okay, that makes sense.
Yeah. Thank you, Kamna.
No, go on.
You too.
Hey.
Anybody else?
It is in right now, but I am submitting a job application right now.
Yeah, so
Well, I hope you get the job.
last class you said that you had to put last class you had said that you had to put a 10-foot pole on a bolt for your car.
Yeah.
Was it the crank pulley or
Yeah,
what was that tight?
it was actually the part that I was trying to get out for the timing chain. So it was like at the bottom of the engine, and I think it said like 695 or 630 pound inches of torque. And I was putting more
Wow.
like 900 and it wasn't budging. So I ultimately, like I said, I ended up using, for starters, I had a 3-foot extension to come out of the wheel well of the front drive of the car. And then I had a 12-inch socket wrench with a 4-foot breaker bar on it. And then I stuck like a 5-foot long barrel of a F-16 or something gun in the end of that and then stood on it.
Wow, that's a lot of torque. I just
Yeah.
was it a diesel or something?
No, it was just a little Honda Odyssey van. You know,
Wow.
when I looked at it, it had some of that blue stuff in the thread. So I think they might have actually stupidly put
Oh,
some of
Loctite.
that thread glue stuff in there. I forget what it's called, but yeah, that might have been the problem.
Yeah, I was really surprised when you said you had to put a 10-foot pole on something, but Loctite makes sense.
Yeah, and not only that, what I discovered was they didn't necessarily do what they were supposed to, obviously, because obviously it was a higher torque. But I even tried like some old shade tree mechanic methods, which I don't recommend. It's actually really dangerous. I had to go back in and connect the actual spark plugs, which you'd actually obviously move so you could move the pistons up and down without any
Yeah.
back pressure. I put them all back in and then wedged a wrench onto the actual nut and wedged it against the body and tried to turn the car over to let the engine do it, and the engine wouldn't do it at all.
Oh, wow. I like
So it
that
was,
idea though.
I thought of that, and I had heard something about it before, and then I went and looked on YouTube, and I found some people that had done it. So and then I was sure that I could do it, and I gave it a try, and woo, it didn't do anything.
Wow.
So it
Well,
actually sat in my driveway for about a week and a half before I finally got it to work. But it really just needed some Mac and Snap-on tools so that I wouldn't break the metal.
oh, I got you. I got you. Well, I was just curious. I appreciate it. You have a good
Mhm.
night.
All right, you too, Randall. Have a good one. Bye bye, everybody.